Welcome to this explainer. Today, we're diving straight into the mechanics of how modern systems are finally, and thankfully, ditching passwords in favor of biometrics and hardware keys. If you've ever felt that sinking feeling of completely forgetting a complex password, or if you're a developer actually tasked with securing user data, you are absolutely in the right place. We are going to explore the cutting-edge standards that are reshaping application security right from the ground up. So let's just ask the obvious question right out of the gate. Why on earth are we still relying on weak, easily stolen passwords when significantly better options exist? For decades, passwords have kind of been the default, but they're a fundamentally flawed system. Why? Because they rely on something you know. And the massive problem with something you know is that it can be guessed, it can be socially engineered, and most commonly, it just gets reused across a dozen different websites. When one single site is breached, your password for every other site is suddenly out there in the hands of attackers. It's wildly costly to store passwords securely, and let's be honest, it is a terrible user experience.
We all know an Alice. Honestly, we've all been Alice, right? Completely exhausted by this endless, frustrating cycle of password resets and delayed security codes. She tries to log in, but can't remember if she used her dog's name or her birth year this time. She tries a one-time password sent via SMS, but it expires literally seconds before she can type it in. She requests a magic link, and of course it gets buried in her spam folder. This kind of friction doesn't just annoy users, it actively drives them away from applications. There absolutely has to be a better way.
So here's our roadmap for this explainer. 1. The end of passwords. 2. Biometrics. 3. Hardware keys. 4. How WebAuthn actually works under the hood. And 5. Implementing the magic.
All right, let's jump into Section 1, the end of passwords. So what's replacing them? Enter WebAuthn. It completely replaces the flawed concept of something you know with something you have or are, using standardized cryptography. Developed by the FIDO Alliance and the World Wide Web Consortium, WebAuthn is the industry standard that makes passwordless login a reality across all major browsers and operating systems. Instead of sending a secret password over the open internet, WebAuthn uses public key cryptography to prove your identity. It ties your authentication to a specific device, meaning an attacker halfway across the world simply cannot log in as you, even if they somehow tricked you into giving up some personal information. Moving right along to Section 2, Biometrics, where you are literally the key. Now, when we break down the various types of biometrics, we see some distinctly different security levels. Fingerprint scanning is incredibly fast and widely adopted on our phones and laptops, though, sensors can wear out over time. Facial recognition is super seamless and hands-free, but its security heavily depends on having 3D depth sensors. Without them, it might be fooled by a simple photograph. Iris scanning is incredibly secure, even more so than fingerprints, but it requires highly specialized hardware. Voice recognition is convenient, but, as we've seen lately, increasingly vulnerable to AI cloning. And palm vein recognition, while extremely accurate and highly secure, is still pretty rare in the wild. The journey from registering your fingerprint to securely verifying your identity really boils down to a fast, three-step process. First up, during enrollment, you register your biometric trait right on your device. Second, when you try to log in later, you trigger the authentication phase where the app prompts you for that scan. And finally, in the verification phase, your device checks the new scan against the stored data. If it matches, the system generates a cryptographic token to confirm your identity to the application. Simple, right? But you might be wondering, where exactly does a scan of my actual fingerprint go? Well, the answer is the TEE, the Trusted Execution Environment, meaning your actual fingerprint image is never sent to the cloud. This is a massive security feature. When you enroll your fingerprint, your phone doesn't just save a JPEG of it. It converts the unique physical features into a mathematical template, a hashed representation, and locks it inside that trusted execution environment, like Apple's Secure Enclave or a hardware TPM. This is vital because, unlike a password, you can't exactly change your fingerprint if it gets stolen. By keeping the biometric data entirely local and mathematically abstracted, WebAuthn ensures your physical identity remains completely protected. Okay, on to Section 3, Hardware Keys. Just tap to log in.
It is absolutely critical to contrast these two approaches, because while biometrics are incredibly convenient, as we just covered, you can't change your fingerprint if it's somehow compromised. Hardware keys, on the other hand, offer basically airtight security. Biometrics face real threats from what security pros call presentation attacks. Think high-quality 3D masks, fake silicone fingerprints, or AI-generated deepfakes designed to trick the sensors. Hardware keys are different. They're like super smart, uncopyable digital vault keys. They don't have a screen, you don't type a password into them, you literally just plug them in via USB or top them using NFC.
And this brings us to a massive, game-changing advantage of hardware keys called origin binding. This ensures your key simply cannot be tricked by a fake website. Imagine you register your hardware key on, say, securebank.com. The key cryptographically binds its credentials exclusively to that exact URL. So, if a hacker sends you a phishing email and you click a link that takes you to a pixel-perfect fake site called fakebank.com, your hardware key will literally refuse to authenticate. It checks the domain, sees it doesn't match the original origin, and stops the attack cold. No human user can be this perfectly vigilant all the time, which is exactly why hardware keys are considered the absolute gold standard against phishing.
Let's look at this brilliant challenge response flow, where the key signs a server's random challenge without ever revealing its secret private key. When you attempt to log in, the application server generates a random value, known as a challenge or a nonce, and sends it to your hardware key. Your key then uses its internally stored private key to digitally sign this challenge. It sends only that signed response back to the server. The server, which already has your public key on file, verifies the signature. If the math checks out, boom, you are logged in. The secret private key never ever leaves the physical device.
Which brings us nicely to Section 4, how WebAuthn actually works behind the scenes.
The true power of this entire system is that it relies on a mathematically linked split pair of keys, completely eliminating the concept of a shared secret like a password. Think about it. When we use passwords, both the user and the server have to know the exact same secret. If the server is breached, the secret is stolen. But with WebAuthn's public key cryptography, a unique key pair is generated during registration. The private key stays locked in your device's hardware. The public key is sent up to the server. Now, the public key can only verify signatures made by the private key. It cannot be used to figure out what the private key actually is. So, if a server holding your public key gets hacked, the attackers gain absolutely nothing they can use to log into your account.
To quote the source text directly here, the private key is never exposed or transmitted, making it impossible for attackers to steal or reuse it. This is huge. It means credential stuffing, where attackers use leaked passwords from one site to breach accounts on another, becomes mathematically impossible. Intercepting the network traffic yields nothing but a one-time signed challenge that can never be reused. This one simple architectural shift literally solves decades of cybersecurity headaches.
Finally, for the developers watching, let's jump into Section 5, implementing the magic. We can break the coding workflow down into these distinct steps, cleanly separating the browser's front-end responsibilities from your back-end server logic. For the front-end registration, developers use plain JavaScript calling the navigator.credentials.create API. This prompts the user's browser or OS to generate that crucial key pair. The front-end then packages up the new public key and sends it to your back-end. Later, during authentication, your backend creates that random challenge we talked about, the front-end client signs it using navigator.credentials.get, and your backend runs the cryptographic verification.
So what does this actually look like for the user when your front-end code executes? Let's think back to Alice. Instead of a clunky password prompt, Windows Security pops up, asking her to confirm her identity, maybe entering a PIN or scanning her face via Windows Hello, just to save a passkey for the application. Notice that it specifically mentions the domain, which in this development case is localhost. The actual user experience is handled natively by the operating system, meaning developers don't have to design any custom UI for the biometric scan itself. It just works.
Behind the scenes, the browser hands back an attestation object and client data JSON. This serves as cryptographic proof, ready to be sent to your backend for secure storage in association with that user's account. Once the user completes the prompt, the attestation object confirms that a real, trusted device actually created the key pair. This prevents software emulators from faking a hardware key. This data is usually base64 encoded and sent via a secure post request to your server, where you'll link the new credential ID and public key with that specific user's database record.
Now, to properly validate the login attempt without accidentally introducing new vulnerabilities, your backend absolutely must perform a few critical safety checks. First and foremost, WebAuthn strictly requires a secure context, meaning HTTPS is mandatory or the browser APIs will just refuse to work. When authenticating, your backend must validate that the origin matches perfectly to prevent phishing and ensure the challenge signed by the client is the exact same one your server just issued, which prevents replay attacks. Finally,
Implementing the actual cryptographic signature verification from scratch is highly risky. The tech strongly recommends using established, proven libraries like WebAuthn for Java apps to handle all that heavy mathematical lifting safely.
We've covered the protocols, the hardware, and the implementation, so the final question is, when will you empower users like Alice by building this passwordless magic into your own systems? The era of resetting forgotten passwords, relying on insecure SMS codes, and constantly worrying about massive credential leaks is finally coming to an end. WebAuthn, biometrics, and hardware keys offer a truly rare combination in cybersecurity. They are simultaneously far more secure and vastly more user-friendly than the systems they replace. Whether you're aiming for the seamless convenience of facial recognition or the bulletproof security of a physical top key, the tools are now standardized, built right into our devices, and ready for you to implement. Thank you for joining me on this deep dive into passwordless authentication. Until next time, keep your origins bound and your private keys locked down.